Now, about the actual topic of why we're here during this hour, 20 minutes. I'll be talking in my part of this first week course on the physical processes shaping evolution of stars and gas and galaxies. Now, in a grand sense, all three of us, Anatoly, myself, and Daniel, will be talking about the same thing. We'll be talking about processes that are involved in the formation and evolution of galaxies. But there are some differences, as you'll notice. Anatoly will be focusing on the structure formation, the origin of perturbation, as he did today, the statistics of perturbation, the evolution in the linear and modeling on linear regimes and collapsing, but based on numerical simulations. Daniel will be focusing on results of numerical simulations pertaining to the physics of baryons as it directly connects to evolution and properties of galaxies. And I'll try to be in between. So we scheduled us sort of in between. I'll try to connect the two threads, the evolution of perturbations and sort of in cosmological context, and the simulation results on the evolution of galaxies by building physical insight to understand how the two are connected and what happens both in simulations that involve just collisionless matter and in simulations that involve baryons, which allow us to get some insights into how galaxies form. So focusing on the physical processes and also physical understanding, physical insights about what's going on. Specifically, this is the topics that I plan to cover, and they are roughly mapped on the number of lectures. So lecture number here is a lecture number, so 1, 2 means the first 2 lectures. And the mapping is, we'll see how it goes. So transition between lectures may be crossing across these topics, but roughly today I'll be talking about mass assembly histories of galactic halos. So here we'll talk about how perturbations evolve in the expanding universe in a cosmological context. And then, so why is it so? First, it connects to the perturbation evolution during early stages in these models that Anatoly was talking about. But second, most importantly, the mass assembly history and mass accretion rate that results from it, from the collapse of perturbations, provides a basis, a groundwork for assembly of matter into galaxies and understanding what happens during galaxy formation, both to dark matter and to the baryons, the baryonic gas. And so after we go through this and understand why matter is assembled the way it is, the way we see it in simulations, we'll start talking about physical processes that are involved in creating differences between collapse of dark matter and collapse of baryons, and particularly dissipation process, gas cooling, gas heating. And the most important, we won't be able to cover all the processes that are relevant. In some processes, we will cover at a level that is relatively cursory, superficial. But nevertheless, I'll try to cover the processes that are the most critical to galaxy formation, and also to give you insight of why these processes are relevant and why they work the way they do, and why they affect galaxies the way they do. We will do so, I will do so by building a simple but physical model for galaxy formation. Model means equations, in particular differential equations that govern evolution of the main components that assemble into galaxies: dark matter, baryons, gas, stars, and so on. And we'll see how inclusion of different processes affects properties of galaxies that come out from such model. And the model is very simple, but as you'll see, it will help us to understand many of the numerical results that we get from numerical simulations. And so after the first couple of lectures, probably 1.5, we'll go through these processes: gas cooling and shock heating processes, star formation, and most importantly, the feedback from young massive stars and supermassive black holes that affect properties of galaxies in a very critical way, and without which we now know we cannot understand galaxy formation. And this will be the last topic, but also the most frontier topics, the topic where most active research in galaxy formation is happening. And this will I will try to make it very clear, but it should come out very clear and loud from Daniel's lectures. Now, before I go on to the topic of today's lecture, let me also say something about the level of these presentations. The level is aimed at sort of beginning or intermediate graduate students who heard something about cosmology. In particular, at least paid attention to Anatoly's lectures. So I'll rely on background results for cosmological from cosmology, because I won't have time to cover them. But in addition to my slides, that will all be found in the GitHub repository that you should have received with the distribution last week. Has everyone received? Who hasn't received the distribution? Can you raise your hand? Everybody? No? From the email. Did you receive a link to GitHub? So that link contained, at that time that when you received it, it contained just information about what I need if you want to run the notebooks, what kind of software you need. And it's not much, the standard Python, and the only non-standard packages are AstroPy and Colossus, which is a cosmology structure formation package written by Benedict Dimmer. Both are very easy to install, and I don't know how many people have tried to do it or how many people have not done it. How many people have not done it? Okay, so if you have any questions about how to do it, I'll try to help you, but again, it's not necessary. You'll be seeing the slides, and you can actually should be able to view the notebooks if you just download them or view them in browser online. But if you want to follow the exercises, and if you want to actually run the notebooks and the codes that you'll find in the notebooks, you'll need to have Python installed and those packages installed, because many of the code that I use relies on Colossus in particular, and also having Python. And again, so some of the information that I'll be using, but won't have time to cover, I include in the form of additional notebooks that will not be shown as slides, but can be found in the repository. And let me say one word about the notation that I use for this. So I'll show you the repository the way it is now. There are some subdirectories that contain codes. So these are Python codes that are sometimes imported into notebooks. These are codes that I either written specifically for this, or some auxiliary codes like numerical integration. But they're essentially Python code living in this directory. Then there is data that will contain data files that are needed, that are used by some of these notebooks. And I will only include data here that is relatively light, so relatively small, like ASCII and so on. I ask you to download a Galaxy catalog from the SDSS Galaxy catalog. That's too big to include into GitHub. It just doesn't make sense. So I just put it in a different place, and you can find information on this in the required software and data notebook here, and with a link to that data. We won't be using it today, but if you will need to download it, I also have it on my computer, and I can give you a USB stick with it. It's not big, but it's too big to put in GitHub. It just could be done, but makes no sense to make downloading the entire repository too slow and bloated. And then images are just some plots that are already pre-made that I used in the notebook, so that's something that you don't have to worry. It's something I include and is used in notebooks. Now, notebooks themselves, you can see that there are essentially the names contain some information about what's in the notebook. And then there is the first few letters and digits. This is BG, means background. So this is information about background to what I'll be talking about. A lot of background comes for the first 2 lectures. The other lectures will not have as many of those files, but these are essentially for your reference. So only if you need to find additional information. Okay, I'll reference some of them in the notebook specifically. You'll find more details in the specific notebook. And this is something you can use to read more on a particular topic, or find something that I won't show you but will refer to. The lecture slides themselves, the lecture slides I'll be showing you today, are in this notebook, and notebooks that contain lecture slides will have L first, so it's lecture, and then 01, it's the first lecture, so it's a first file, right? And then it provides some information about what's in the lecture here. And then X here, X01, these are exercises. So right now I added one exercise which will be related to the topic of today's lecture and tomorrow's lecture, that you can try to do this afternoon or tomorrow, and I'll mention some of what's involved there, but it's already there. It's just one exercise, and relatively straightforward, relatively simple. The exercise I'll provide you, most of the code that you need to run them will be provided, so the amount of coding that you'll need to do will be minimal, although it may be non-trivial if you're not familiar with Python. Then you'll need to learn, but there is not much coding that will be involved. That exercises are designed to be mostly run and thought about, but not coding. Any questions about these practical things? No? Okay. I'm pretty sure by experience there'll be questions later, so let's go on. Okay. So today, lecture 1, as I said, it will be mass accretion histories, mass assembly of halos, of galaxies and parent halos. Mostly we'll be talking about mass assembly without differentiating what mass we're talking about. It's mass of matter. So we should think about it as both assembly of dark matter and baryons. In the models, in the standard model structure formation that we work with when we try to understand galaxy formation is so-called cold dark matter scenario, in which matter consists of a mix of collisionless dark matter, or at least weakly collisional, and collisional baryons normal matter that, of course, can dissipate, right, and undergo all kind of complicated processes. If you heard thunderstorms last night, it's a very complicated process that mostly involves baryons. And dark matter, if it exists the way we think it does, was just streaming past quietly without noticing any of these calamities. So baryons are very complicated, and that's what makes galaxy formation both challenging, fascinating, but also very difficult. Dark matter collapse is much better understood. But for this purpose, we'll just talk about collapse of matter without differentiation. We'll start differentiating later, when we'll start talking about processes involving in galaxy formation, and then we'll try to see what's different about dark matter and what baryons do it. Right now, we'll just consider their joint collapse. That collapse happens from a perturbation. In order for something to collapse, we have to have an initial density perturbation. And also, for perturbation can be both positive and negative, and those are both perturbations. So let's talk about this for a little bit. So when we talk about perturbation, we talk about deviations from the mean density of the universe. The mean cosmology, the mean expansion of the universe, is defined by the mean density of matter, right? So this is denoted as raw matter mean, and that again includes both dark matter and baryons. It's all matters that exist. And then locally, if we look at a field means a function which is a function of position, of location, either in space, like what we do now, or phase space of velocities and positions. But right now we're looking at a function which is a function of space coordinates, so it's a function of location in space. So density here, rho, is specific function which is a function of location, right? So it's rho of some location x. And we're looking at a field, instead of using rho, which is dimensional quality, we're looking at dimensionless quality called density perturbation, which is defined as the density minus the mean density of the universe divided by the mean density, right? So it's a dimensional quantity that tells us how locally matter deviates from the mean density of the universe. And if we look at it, if we set density to 0, if we find a region that's completely empty in the universe, then the delta will not be 0, it will be -1, because if rho is 0, we just have minus rho mean divided by rho mean. So on the lower edge, delta is bounded by -1. That's the lowest value it can have. On the upper edge, there's nothing to bound it, so it just will be determined by the maximum rho. So delta in the upper tail can be whatever. And delta in this room is very, very high. It's something like 10 to the 30th, I think. Because the mean density of the universe is 10 to the minus 30 or thereabouts, whereas, say, my body is 1 gram per cubic, 10 to the minus 30 grams per cubic centimeter. My body, which is mostly water or something like this, or the sun, is about 1 gram per cubic centimeter. So there is 30 orders of magnitude in density difference. So something happened between the cosmic microwave background that we see having perturbations in matter to be fraction of 1,000 or even less than that. And today, when we see perturbation that has 10 to the 30 amplitude, right? The process that involved in galaxy formation, which we are kind of one of the consequences and one of the ends, resulted in a growth of delta in about 13.8 billion years of 30 orders of magnitude. So it's a lot, right? But we think that it all started, and this is also what we see in the cosmic microwave background temperature fluctuations. It all started with a Gaussian, isotropic Gaussian field, examples of which are shown here. I show you two fields for a reason that will become clear. One of the fields, the left panel, shows you a realization. It's a random realization of a Gaussian, isotropic Gaussian field in a region of 6 H inverse megaparsecs. Forget about H inverse if you don't know what it is, but it's just think about this 0 to 6 in megaparsecs. This region is from 0 to 60, so it's a region of 60 megaparsecs, so 10 times larger. But look carefully. Can you see it well at the back? So are they similar or are they different? Similar. They're very similar. Everybody agrees? Okay, let me rephrase the question. Can you see any differences? Yeah,
yeah, small differences.
Sounds like the point structure.
So which differences? Just shout. What differences do you see?
The contrast maybe. The contrast maybe.
There's bigger contrast in the left image.
Yeah, there is some difference in contrast, and I heard somebody say there is a difference in fine structure. Now let me first explain why they look so similar, right? I told you there's a random realizations of isotropic Gaussian field, but they're random, and so I used a random number generator to generate these. And by the way, in one of the notebooks, one of the background notebooks, you'll find code that generated these. So if you're curious of how a Gaussian field is generated with lambda CDM power spectrum with the correct statistics specific to lambda CDM, you'll find the code that generates. As for many other plots that you'll see here, you'll find in one of the notebooks, you'll find the code that produces them. Not everything, but most of it. Right, so the reason they're so similar is because I use the same random seed in both cases. So I use the same cosmology, and I use different boxes, and I use the same, I generated this Gaussian field delta on a fixed grid, because numerically I have to do it. I have to use some sort of grid to sample the field on the same size grid, 256 cube. That's because Python makes it very difficult to go beyond that. So possible, but painful. So it's a compromise. So 256 cube, so the grid is the same. But the box size, that's said, physical box size, or Kamunin rather, is 10 times different. And so I use the same random seed, and that's why the statistics, where different peaks are located, looks similar. But as you noticed, because it's something that is visible, it's something that you can notice visually, there are differences. And the first difference is in sort of overall amplitudes of peaks. The second is the amount of fine structure that you see. And I should say that the color scale in both images, so I have to normalize the color scale to tell it which colors correspond to what over densities. It's different in two panels, because if I made it the same, one of the panels, depending on which ones I would make to look nice, one of the panels would not look very good, because the range of actual over densities is different. So they're both, the color schemes are normalized to the delta mean and delta max specific to the region. So in each of these shown regions, I determine what delta mean and delta max is, and I define the range of colors relative to specific delta mean and delta max of those two regions, okay? So I took out the overall difference in the amplitude, right? We'll come back to that overall difference, just to show you but even after I did this, right, there's still, say, if you look at this peak here, right, and the corresponding peak here, you can see that there's different color brightness, different amount of green there, right? And then with a small scale fine structure, if you look at the dark region, dark blue region here, by the way, the bright regions here, although for this field, it doesn't matter which one is which, right? And why it doesn't matter? So I could have told you that the dark regions are positive delta and green is negative delta. It's actually the opposite. Green is positive, dark is... But for this field, it actually wouldn't matter. Why is this? Yeah, it's a Gaussian. It's a symmetric field. And the Gaussian field, when we say Gaussian for a field delta, we really just mean that PDF. What happened to that blue? I stole. Can we get the light? Really what we mean by Gaussian is that PDF of delta is a Gaussian. It's a Gaussian PDF. So it's 1 square root of 2 pi, some sigma, minus delta squared, sigma squared. And because delta is defined with respect to the mean density, by definition, mean delta is 0. So we don't have to worry about the mean. But otherwise, it's just a Gaussian PDF. And that's all we mean. When we say isotropic, it means that the field is the same everywhere statistically. So first, it means that it can be specified by statistics that's just a scalar function of separation. And second, by the way, you'll see this again in a couple of slides, so don't worry. It's just a Gaussian, nothing complicated. The statistics of the field can be specified by scalar separation, so we don't have to worry about direction on the sky because the field is the same everywhere. And when we say Gaussian, it just means this. So it just means that PDF of the delta field is Gaussian. And it's symmetric. The Gaussian is a bell curve, right? It's symmetric around 0. It's symmetric around. So what it means is that it's a fraction. It's a PDF of delta, which means that you can interpret it as a fraction of volume that corresponds to a given value of delta. And because it's symmetric, it means that the fraction of volume in the negative deltas is the same as the fraction of volume in positive deltas. You can kind of see this in this picture, right? The fraction of, in this case, area, but in 3D would be volume, occupied by blue and green is roughly the same because the field is Gaussian, right? Right. So I didn't have to tell you this, but if we focus, the blue is actually underdense, and if we focus in this underdense region, we see that here it seems to be filled by some greenish fuzz, greenish small-scale structure, whereas here it's present but not as much. And these subtle differences in small-scale structure reflect the fact that on different scales, the statistics of this Gaussian field in this model are not quite the same, right? And this will become important for understanding the differences between formation of collapse of galaxy clusters and collapse of smaller galaxies. And the differences that are connected to the difference you saw there will be subtle, but nevertheless it's worth to be aware of them. To understand where those differences come from, let me go back to statistics of a field, some of which Anatoly already touched on, and but here they'll be specific to what I'm talking about. So usually when I said that we work with field delta, that is function of position only, and it's a Gaussian, so it's described by Gaussian PDF, but most generally we work with a smoothed field. So we work with a field on a given scale. Even when I showed you the previous slides, I told you that there is a finite grid on which I sampled the field of 256 cube. It means that there is a smaller scale on which you can resolve the delta. So there is a smoothing scale corresponding to one grid cell that was involved there, although it was hard to see on this plot. So usually we are working not with the field delta directly, unsmoothed one, but with some smooth version where we take a field delta, the usual convolution. You take a field, you convolve it with a filter where all the small scales are filtered out, and you get a filtered delta. This is a linear operation, so if delta is Gaussian, this is also Gaussian. So delta filtered delta is also described by a Gaussian PDF. But now, both the delta field is a function not just of x, but as a function of the smoothing scale on which we're doing this, on which the filter depends on. And so is the RMS fluctuation of the field. Also depends on the scale, because as we're averaging, you can kind of guess that as we average on a larger radius, when our radius becomes large enough, say 100 megaparsec or gigaparsec, we better get the mean density of the universe, right? So we better get to delta of 0. So, but on small scales, the delta could fluctuate, and so clearly the amplitude of fluctuations on larger scale, on the gigaparsec scale, should be pretty small, because in any gigaparsec scale region, we should be getting density very close to the mean density of the universe. So sigma, from just general qualitative considerations, should depend on scale. And it's tightly connected to the power spectrum that Anatoly already talked about. In fact, it's just a filtered power spectrum. So if we take P of k and multiply it by a Fourier counterpart of this filter that we're using, squared, and integrate it over k-space, this is a standard convolution. The convolutions are easy to do in Fourier space because they correspond to just multiplication rather than taking the integral. And so that's what we're seeing here. In order to figure out the typical fluctuation amplitude on the scale r, we're taking the power spectrum that has no smoothing, just describes the fluctuation on a particular scale in a model. We convolve it with a filter, in this case squared, because power spectrum measures square of the amplitudes. So convolution means that we're multiplying by filter squared, and integrate it over k-space. The k is a wave number, it's inverse distance, and k in 3 dimensions, it's inverse scale cubed, or inverse volume. The filter is dimensionless, and so it tells you that, and this quantity is dimensionless because it describes the fluctuation of delta. It tells you that the power spectrum should have direct dimensions of volume because the volume element in k space is inverse volume. So we have to multiply inverse volume by volume to get a dimensionless quantity, right? So power spectrum, it has dimensions of volume, and that's why often when you see it plotted, in fact, if you probably didn't notice or didn't pay attention, but if you go back to Anatoly's slides on the y-axis, when it shows P of k, you will notice that it has units of volume. And that's why, because P of k is integrated over k space, and there's no dimensional quantities here except for P of k. And for the filter, you can choose, people choose different things. You can decide to filter in a different way. The filter that I'll be using, and that is most frequently found in the literature, and also the most intuitive to understand, is so-called top hat filter, real space top hat filter. And all it does is that it just takes a point. So if I'm interested in a delta field around a given location, I draw a sphere of radius r, large R, around that point, and I just measure the mass. I just measure mean of a density within that volume, and that's my smoothed quantity, right? So the smoothing operation is just averaging within the sphere of radius r in real space, right? That's what this means. So if I'm within the sphere, I'm averaging. If I'm outside, I'm not taking anything. And this factor just normalizes and makes this quantity dimensionless, and also normalizes it to unity, so it integrates to unity. Its Fourier counterpart is this, some trigonometric function, and actually is a very funky function with ringing, and that's because this function has a sharp edge. Usually when you deal with functions that have sharp edges, because Fourier transforms are interpolations, effectively, the Fourier coefficients tell us which coefficient we should use in a trigonometric series to approximate the function. So if we try to approximate a function that has a sharp edge with Fourier harmonics, the sharpness of the edge requires many, many harmonics. So it usually spreads the Fourier transform over a very large range of k, and that's what happens if you plot this function. It looks like a peak on a particular scale, but then many, many ringings corresponding to that sharp edge. So sometimes people use something like this, but with a smooth edge, where this essentially is a top hat, but with a sharp but relatively soft edge to compactify the function. But that's already technical detail. Mostly what you'll find in these lecture notes and throughout the literature is people use this. And it has very intuitive understanding because we're averaging within a given radius. And also, there is a mass that can be associated with that radius, with that scale, that is just given by 4 pi over 3, mean density of the universe r cubed. Right. So we can either talk about the scale, or we can talk about enclosed mass. So when we talk about collapsing peak centered on some high density region, we can also talk about the mass that associated with that peak that's enclosed within the radius r, right? And that's usually defined using this equation. So here's the actual calculation. Again, you'll find code that computes this, just taking this integral numerically in one of the notebooks, and it shows sigma as a function of r, as a function of scale, for a lambda CDM cosmology. The same cosmology that was used to generate those fields that I showed you. And you can see that, well, it's a kind of a boring function, right? It's dimensionless. Again, there's no dimensions here because it enters, it's just like delta, just describes the fluctuation of delta, so it's dimensionless, fluctuation of dimensionless quantity. And it's featureless, in almost a power law. You can roughly even approximate it by a power law, but it's not quite a power law. It has a roll to it that reflects the fact that power spectrum itself, to which it's related tightly through an integral, is not a power law. But which scales here correspond to galaxies, relevant for galaxy formation or formation of collapsed structures? In order to do that, we can essentially connect the mass and radius the way I described. And in general, when we talk about collapsed structures, the collapsed structures they're not just structures on mean density, they have some radius associated with them. And so the mass and radius are connected through additional factor that describes the overdensity within the radius r. But at early times, the reason we can do it so interchangeably between mass and radius and actually use this equation to define the scale is because when we deal with initial perturbations, they can be arbitrarily small. If we go back far enough in time, we'll find that delta is very small. For example, at the redshift of cosmic microwave background, so redshift of 1100 or so, these fluctuations have amplitude of 10 to minus 3, 10 to minus 2, so 40%. So if we neglect delta, it's just 1% difference. But we can also just go back further in time and where delta can be negligibly small. And so we can define a mass or corresponding or for a given radius or a radius for a given mass that are related by this equation, in which case the mass and radius are called Lagrangian mass or Lagrangian radius of the perturbation because they essentially describe the comoving extent of the perturbation when it was very, very small, where the delta could be completely neglected. Right? So either way, so using this equation, we can relate the scale to the mass. There are some cosmological parameters involved. And if we do that, we'll find that I show you equations. You'll see that, for example, the 1 megaparsec here, right, if we use r, so sphere of radius 1 megaparsec, which means the total extent of about 2 megaparsecs, the mass that corresponds to that is 5 times to the 11, right? So it's close to 10 to the 12, which is thought to be the total mass, total collapsed mass associated with the Milky Way galaxy, with our home, right? So that's why I chose this scale, right? Because it gives me something, it's a round number, but also gives me something close to the Milky Way mass. Then if we say I'm interested in galaxy clusters that have typical masses from 10 to the 14 to 10 to the 15 solar masses, so let's take 10 to the 14 because it will make it simple. So 10 to the 14, it means that, or 5 times to the 14, let's say. It means that I have 3 orders of magnitude in mass higher. In order to get 3 orders of magnitude in mass, radius comes as cubed. So I have to go 10 times larger in radius, right? So then 10 cubed will give me 3 orders of magnitude of mass. So to get 5 times to the 14, r will be 10 megaparsecs. So going back to these fields that we looked at already, this region with a peak like this, which has size of about 2 megaparsecs, or radius about 1 megaparsec, will collapse into a galaxy with a mass between LMC, Large Magellanic Cloud, and the Milky Way. Whereas a corresponding peak in this region, which has size of about 20 megaparsec, or radius of about 10 megaparsec, will collapse into a galaxy cluster like Coma, right? Just because those differences in size correspond to a different amount of mass that these peaks have associated with them. Is this part clear? Any questions? Right. So we're just setting the stage to understand what scales are involved. And also, actually, so let me go back to the sigma. So this allows us to also just pick scales that are relevant for formation of galaxies and galaxy clusters. So this is r, so this is radius. So for clusters, the scales that are relevant are about 10, so roughly here, right? And then everything below will be associated with either groups of galaxies or galaxies down to whatever smallest mass is relevant for galaxy formation, right? So the range of scales that are relevant for collapsed objects, so formation of galaxy clusters and galaxies of all masses, will be simply associated with the perturbations that have size of 10 or smaller here, right? And you can see over this range, so these scales are irrelevant for collapsed objects. They're relevant for cosmic web, but not for structures like galaxies and galaxy clusters. And so we're interested only in galaxies and galaxy clusters. This is the range we're working with, and you can see that over that range, the sigma is even much better approximated by power law. Of course, if we shrink the range of function, right, at some point we can approximate it as a linear function, as a power law. This is log-log, so, right? So linear means power law. And so we're just restricting the range, but it also reflects the fact that the slope of the function is not changing rapidly, right? So it's relatively shallow change, very smooth change. And so this is the reason why the difference in the small scale structure, statistical structure in those two fields looks so subtle, right? I told you that in these fields, let me see, let me go back, I forgot which one, here. I told you that I took out the main difference, so because I normalized each to its own range of delta mean and delta max, it means that I took out the main difference in delta amplitude of the two regions. The only difference that you see here, the way they're plotted, is the difference in statistical distribution of typical amplitude between smaller scale perturbations that are visible and larger scale perturbations that are visible. And you can see that the difference is subtle, right? Because you can see it, but it's first thing you notice is that they're very similar. And only if you start to look a bit more, you find that there are subtle differences. And so these subtle differences reflect the fact that the slope of this function is not quite a power law. If it was pure power law, then you wouldn't see any difference, right? They'll look to you exactly the same in these plots. The fact that you see a subtle difference just reflects the fact that this function has a role. So in different scales, it has different slope. Right. Why am I harping on this? Because this is the main difference in the formation, well, the subtle difference in the formation of galaxy clusters and galaxies. The biggest difference between them is the fact that the actual value of sigma is different on different scales. So on cluster scales, it's about, if we draw 1, we see that it's slightly less than 1. This is a field extrapolated to redshift 0 linearly. It means that if I take a typical fluctuation at initial redshift and some, whatever I choose it to be, maybe CMB redshift of 1100 here, and I linearly extrapolate, means that I divide it by gross factor normalized to unity at redshift 0. This is a solution of a linear equation that Anatoly was talking about. And also, it's, if you're interested, you'll find the derivation of this equation and how these factors come about in one of the notebooks on linear perturbations that is included in the repository. This is extrapolated to redshift 0. So initial RMS is divided by the gross factor between initial redshift and 0. And so this is how the typical fluctuation would look like if fluctuations would grow linearly and evolved up to redshift 0, right? So what does it mean? It means that on cluster scales, so scale of 10, fluctuations are a few tenths, so they're not quite 1, but few tenths. It means that fluctuations become of order 1, and it means that, well, you're maybe still in a mildly nonlinear regime, but linear theory should not apply to them, right? Because delta is no longer much less than 1, which is an assumption that goes into linear theory in the derivation of this linear equation. And on the scale of galaxies, we can see that delta is already, the typical fluctuation is above 1, which means that linear theory should have completely broke down by now, and this object should have collapsed because that delta is already sizable, it's already nonlinear. Right. And the main difference in the evolution of galaxy clusters and galaxies is this difference in typical amplitude at a given time that is given by this function, because it determines how frequent, given the PDF of this delta field is Gaussian, it gives us information about how typical, how frequent is a given perturbation on a given scale. So it means that perturbation of order, say, 5 on a cluster scale is very rare, because it's many sigma away. On the smaller scales that are shown here, perturbation of 5 is maybe 1.5 to sigma, so it's not very rare, right? So, and the line itself tells us what is a typical 1 sigma fluctuation in the field. Again, the main difference between clusters and galaxies, scale objects that we'll talk about in the terms of their collapse, is this difference in the overall amplitude and different scales. So different galaxies have different amplitudes, different size of galaxies, different R and different masses, have different typical amplitudes. So as we go up to smaller and smaller galaxies and smaller scales, the typical amplitude increases. And so it means that the typical perturbation amplitude of a smallest collapsed object is higher. As we'll see, the perturbation amplitude is the main thing that determines when they collapse. And so the small scale things in such models collapse first because they have higher typical amplitudes. And as we go up in mass to galaxy clusters, the amplitude grows smaller and smaller and smaller, and the typical collapse time will be later and later because of this. And then the second difference, but it's much more subtle, is a difference in slope, which defines the typical amplitudes of other structures that are forming as big collapses around it. And that creates a subtle difference, but nevertheless is an important difference. Okay, so enough about the actual properties of perturbations. How do they actually collapse? The most accurate answer, also the most accurate and also the most pleasing, because we can look at it in great detail in 3 dimensions and make nice movies, is numerical simulations, cosmological simulations, where we start with a realization of a Gaussian field of the kind that I showed you. We sample it either with particles or, well, mostly with particles, or in case of baryons, sometimes with a field defined on the grid. And we integrate numerically the evolution of this field forward in time without making any assumptions except some assumptions about numerics on the smaller scales that define resolution effects. But otherwise, we are getting the result as accurate as we can if we keep the resolution effects under control. So direct numerical simulation, there is a great workhorse in the great tool that is used and to which majority of advances in our understanding of how structures form, how they collapse, it came about. So let's start with that and let's look at how such fields evolve in numerical simulations. And I'll start with showing you how perturbations evolve in a region of 60H inverse megaparsecs. So one of the regions that I showed you in the beginning, so the region on the right, 60H inverse megaparsec in lambda CDM cosmology. In this case, you'll see a movie that starts at a redshift of about 20, although in 20 it's mostly dark because the color here corresponds to the delta field. So when delta is very small, close to 0, the color is essentially neutral, it's dark, it's transparent. And when delta becomes large, so negative regions, the more the regions closer to -1, the more transparent and dark it is. And 0 is almost dark here, so you won't be able to see it. So any region that you see which is actually colored has positive delta. And the color, the brightness and the intensity of the color is proportional to the logarithm base 10 of delta. So it's logarithmic scale. When we start at 20, the box will be mostly dark because the perturbations are very small. And so at redshift 10, you start seeing some perturbations, and you can see it here. So I'll walk you through and I'll show you the movie. But you'll be prepared to what you're going to see there. At that point, if you look at this perturbation field, which is shown in 3D, it actually still looks pretty Gaussian. Not in detail, not on small scales. But you can still imagine that this field corresponds to a Gaussian noise. Because it's not very obvious. Like we said, one of the properties of a Gaussian field is that the fraction of volume in positive delta regions and negative delta regions is equal, right? And it's not very obvious that it's not for this field, right? It still looks like mostly like noise. But as time goes on, so this is redshift 5, so about 5 billion years after the Big Bang, and then redshift 3, redshift 2, 1, and current moment, we see that the field becomes progressively non-Gaussian. So nobody probably who knows anything about the random Gaussian fields would claim that these fields look Gaussian, right? I hope not. Do you agree? Yeah? It doesn't look like noise, essentially. That's what I'm saying. Definitely not Gaussian noise, but not like any noise. It has structure, and this structure is called large-scale structure. People use the term cosmic web or large-scale structure of the universe, and it is because it is structure and it's not Gaussian, it's not noisy, right? And the only thing that's in between here is gravitational collapse. So it's gravity acting on initial Gaussian perturbations and making them into this field. As we'll see, numerical simulations tell us that this happens, that the cosmic web emerges from a Gaussian field. But why it does so, we'll touch upon. It's actually not that difficult to understand, even without solving any equations or any numerical equations. But the result of gravity acting on perturbations on scales of tens of megaparsecs is to turn a Gaussian field into a highly non-Gaussian one, in which most of the volume is occupied by empty regions called voids, and then some small fraction of the volume is occupied by collapsed objects that are shown, can be seen as peaks in color, and also some structures, some linear structures, or maybe flat structures that connect them, called filaments and sheets. So let's look at how this happens in dynamics, so it's in motion. So in this case, in addition to evolution, you also see that the box will rotate. This makes things a little bit more confusing, but it also allows you to see the three-dimensional structure of the distribution much better. Because rotation in our brain is interpreted as, our brain converts it into 3 dimensions, so you'll see it, the shape of the structure is better. And I'll show it a couple of times to highlight different things. So first of all, the initial collapse went very fast, but if you focus on it, it looks like a Gaussian field just gets brighter without changing much. And again, it's very fast, so so pay attention when the movie starts again. Here, you see that initially it just kind of appears from very, very dark to something that's developing like a photograph in the old development style. And that's because in this case, on these scales, the evolution is still mostly linear. And linear evolution predicts that perturbations on different scales evolve at exactly the same rate. So the Gaussian field just gets higher contrast, so delta grows, but it grows at the same rate on all the different scales. So in initial imprinted Gaussian field just gets brighter, 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 higher, but it doesn't change very much. That stage lasts for first few frames of this movie, and then very quickly you see a cosmic web developing. And how it develops is kind of difficult to glance from this movie because a lot of different things are going on at the same time, plus the structures that form are rather complicated, convoluted, reflecting the different peaks and valleys and the presence of structure on different scales in the initial Gaussian field. But one thing again, so there is collapsed objects, so galaxies, clusters, the peaks in this colored field. Most of the volume at late times is occupied by empty regions, voids, and there are filaments, and you can also see that in 3 dimensions, when you see the shape of these structures, many of them, like here, for example, when it rotates, you can see that many of these filamentary structures and many of the collapsed objects are actually concentrated into a flattened structure, which has size comparable to the size of the box. So it's like a sheet. It's a collapsed flat thing. And sheets actually even more prevalent than the filaments in this field. So usually we talk about, because we see in projection that distribution of matter appears linear on these scales, but if you look in 3 dimensions, many of these linear structures actually turn out to be flattened sheet-like structures. Why this happens is also we'll touch upon.
Excuse me.
Yeah.
Can you back to the previous slide?
Okay. Yeah. This is what I was about to do. Yeah.
Is there 100 megaparsecs? Is there like a final size or the first one? So
Okay, good question. So I told you that it's 60. So it corresponds to the box size that I showed you in one of the frames, which was 60 h inverse megaparsec. H is about 0.7. So 60 by 0.7, it's not quite 100, but it's close. So here I just rounded it. It's roughly 100. And it's a very good question because I should have highlighted this. You can see that the box in these frames does not change, right, in size. It just shows you the same size. This is so-called comoving coordinates. So it's coordinates in which expansion of the universe is taken out. So this box in which you see evolution of structures is actually expanding with the rate at which universe expands. But because we know that expansion is an analytic function, we just take it out. Because if I didn't do this, the box between redshift 0 and redshift 10 would be different by a factor of 11 by 1 plus z. And you wouldn't see much what happens in such small box. And plus this is a trivial expansion which is given by background cosmology. So when we focus on formation of structure, we usually take it out, not always, but usually, and work in so-called comoving coordinates, which comoving with expansion of the universe. So the box size here is comoving box size, where expansion of the universe is taken out, and so you see what happens to that box as it expands in the universe, where as always box is not changing. Was it?
It is start or final?
Well, when it's comoving, it doesn't matter. It's the same. So comoving means that it will be the same at all redshifts, because the only thing that's different between these redshifts is just expansion of the universe, and I took it out. When I took it out, there's nothing else left except for rearrangement of matter in the box, but the matter in this box is conserved, so the mass inside the box stays constant, right? As the box expands with the universe, it just expands with it overall. Did that answer the question, or is it still confusing? By the way, can you still hear me? Yeah, in the back? Okay. Any more questions about this? Yeah.
What are the boundary conditions?
Periodic. You can question the validity of such periodic conditions, especially when the boxes are relatively small, but this is a standard condition in such simulations, and it's motivated by the fact that the field is isotropic and uniform, supposed to be uniform at larger scales. When we work with boxes like this, which are kind of borderline, the mean density of the universe is not quite, doesn't have to be exactly mean. And so the box does not have to expand just like expansion of the universe. In standard simulations, when people run such boxes, the expansion is still forced to be the mean expansion of the universe. So we're forcing the mean density in the box to be equal to the mean density of the universe. Nowadays, there's no particular reason we can actually abandon this condition. And if you heard about so-called separate universe simulations, those simulations actually allow the mean density in the box to be different from the mean density of the universe, and we evolve the box as though it would evolve under a certain overdensity, still in the same background cosmology, but the box is allowed to have deviation from the mean density. So that's again technical detail, but it can be done. In this case, the density is just forced to be the mean density. Okay, so this is just overall how cosmic web emerges under the action of gravity on these scales, on tens of megaparsec scales. And by the way, we said that on scales of 10 megaparsec, so about 1/10 of this box fractions, big fraction of the box, a cluster should be forming. So you see that objects like this are forming on a scale that assemble matter from a very large region, sizable fraction of the entire box. And so these largest collapse peaks, here and here, they correspond to massive clusters and groups of galaxies. The smallest peaks that you can barely see in this distribution on these scales, those are objects that are 10 times smaller that correspond to formation of Milky Way-like galaxies and smaller. But yeah. So let's look at a smaller box. Something happened to my, let's see. Okay, yeah. So right now we'll focus, because it's kind of hard to see formation of individual halos on the scale that you were showing. Let's look at how individual peaks collapse. So we're dealing with peaks in a Gaussian field that have complicated structure and also structure on all scales, because you saw that sigma, delta is present on all scales, and sigma is just smoothly changing function of scale. So when we look at a region of a given size, we have perturbations on different scales superimposed on each other, and they kind of all evolve, co-evolve in parallel and interact with each other. So again, when we look at redshift 10, we see that on these scales, on the scale of entire box, the field looks kind of like Gaussian, but when we focus on individual peak, it's already non-Gaussian. So we see a big presence of big empty regions, voids here, because in this region, on smaller scale, the gravity already had time to act and do its job and turn the initially Gaussian field into non-Gaussian. And the peaks that's collapsing, you can see that there is a peak, and it has complicated structure, but it has a particular density and mass associated with it. In this case, the scale is just a few megaparsecs. So think about it as a collapse of a peak in the left part of the Gaussian realization that I showed you. And the small scale structure here is collapsing first because it had typically a larger amplitude, as the largest peak is still collapsing at this redshift. Then as time goes on, the peak collapses, different parts of the peak collapse into small peaks that then coalesce and go through the process of merging to form a final object here that you can see at redshift 0, right? Now I didn't tell you the mass of this object. I told you, well, you can think about it as a collapse of a peak on the left, but in principle I didn't tell you what is the scale or mass here. And the reason is, once you've seen a collapse of this object, which I'll show you now, you've seen them all, for the reason that we'll discuss shortly. So let's look at it in motion. No. Yes. Again, lots of things going on, so we'll go through it a few times to see what happens. The first initial collapse was very fast. Lots of things merged together, and then at late times the collapse slowed down, but there is several merges. So here a lot of different things collapsed in sequence and formed a couple of massive objects that then come and coalesce at some point. So these are so-called mergers. And then you see a lot of small things that formed from small scale peaks zooming through and surviving to redshift 0. And overall, it forms in the end an object, a collapsed object, with lots of substructure, so-called. So there's diffuse matter, and then there is substructure. Overall, the impression is that there is lots of complexity there, right? There's lots of things going on. So we're getting an exact answer, but it's quite complex. So throughout the rest of today and beginning of tomorrow, we'll try to make sense of what's happening. So I'll show you what happens for the collapse in terms of statistically, not in movies, but in some measurements in this type of simulations, and then we'll try to make sense about what's going on visually. But it does look complex. To preview, I'll tell you that, well, it does look complex when you look at these movies, but it's actually quite simple. And you can understand it from intuitive physical reasoning, most of what's going on here. This complexity just reflects the fact that we have perturbations at different scales, but the actual physics of what's going on is relatively simple. Right? And that's something that's worth keeping in mind. To get answers, to get precise answers, we need simulations, but it is possible to understand what's happening in simulations despite the apparent complexity. Any questions about this one? Yeah?
It seems like filaments disappear in last image.
Yeah. Most of the filamentary structure that you see, if you follow what's happening, the question was, it looks like filaments that were present at early times are disappearing. There is one filament that you can still see because the image rotates, and when this object rotates, you can see there is still kind of a filament between them. But it's true that majority of the filamentary structure that you see at early times collapses, and all the matter that was in those filaments actually ends up in collapsed halos and collapses into one single object. So a lot of filamentary structure that was present in the early times ends up in the Milky Way. So if you want to, or an object that forms in this model. So if you think, if you want, you can think about running this movie backwards in time. So think about our Milky Way that has a halo, say 300 kiloparsec in extent. And if we were able to see a movie, how it formed, it would unfold at reaches 3 to 5 into some complicated structure that will have many different filaments in which different galaxies would co-evolve, and all of that stuff would assemble into our final Milky Way. So formation of a galaxy like the Milky Way is a result of a formation of many parallel processes in different regions, but neighbor regions in the universe, that then all get assembled into a final object, including the filaments. And we'll talk about the filamentary, how filamentary flows onto galaxies form and actually affect the evolution of gas when it accretes into galaxies. Any other questions? Okay. So I told you that I didn't tell you the scale of this object, and that's because once you've seen the formation of such object in matter without any baryonic processes, you essentially seen them all. Because again, the main difference between these formation of objects on different scales is just a relative amplitude, but because the sigma as a function of r, it's almost a power law, it's a very shallow function. The fact that this Gaussian field on two different scales look very similar to each other means that when we just look at dissipational collapse of different peaks without any dissipational processes, the structure of collapsed objects looks very similar. So in these two images, which I like to show because they make this point very clear, you see a density distribution, again with color showing the logarithm of local density of matter, in collapsed objects of two different mass. It is different by 100 orders of magnitude. But without knowing which object is which, it would be very difficult to tell. And I've tested this on many experts, including Anatoly, who I asked to guess which object here is which mass. And the answer is usually 50-50, which means that people are guessing. So it's a pure random guess. For some objects, if you look really, really careful, there are telltale signs which can tell you which one is which. But in this case, it's impossible to tell because internal structure of collapsed objects reflecting the fact that the power spectrum, so amplitudes of objects in different scales, almost a power law, is almost self-similar. And so if collapse of dissipationless matter was all that was going on in the universe, objects on different scales would collapse very similarly and would have very similar structure, and this would be the end of the story. But we know that galaxies behave very differently. If I showed you a galaxy and I showed you a galaxy cluster, there will be no way I could fool you because galaxies look very different. The galaxy that forms an object like this and galaxies and distributional baryons that form in a cluster like this have very different properties and appear visually very, very different. And so the actual devolution of baryons is highly non-self-similar, and the difference between formation of collapse of dissipationless matter and collapse of actual galaxies that involve a lot of dissipational processes is a subject of galaxy formation study. Right? But in terms of collapse, things are relatively simple. So they're relatively straightforward. Yeah?
Which kind of galaxies are forming after this process? I mean, spirals, ellipticals, radials?
So here we don't. in principle, we don't know because we're only looking at collapse of matter. And here, like I said, we should be thinking of that I'm showing you collapse of matter that is a mix of baryons and dark matter together. But both baryons and dark matter are assumed to be dissipationless in this simulation. So this shows you what would happen for the overall distribution of matter, or for the dark matter only, if there would be no dissipation. Of course, the fact that baryons do not look the same, they look very different on the different scales, means that this assumption for baryons is very bad. So for baryons are experiencing dissipational processes. And that's what we're trying to understand, what makes a galaxy different. So in this object, a galaxy would form. And the mass of this object makes it difficult to answer your question, because about 50% of objects of this mass have elliptical galaxies forming, and about 50% form spiral galaxies. For example, this mass is not that different from what we think Andromeda mass, Andromeda galaxy. And it's a spiral galaxy with a big bulge, so it's kind of in between spiral and elliptical. The Milky Way is maybe somewhat smaller, but it's not that different. So that kind of gives you a sense what kind of galaxies form in this halo. This is a mass that's close to the mass of the Virgo cluster, one of the nearest massive clusters to the Milky Way. And this would form a cluster of galaxies. Actually, just to tell you, this is this object. So this is 10 to the 12. This is a cluster. And so in this object, what we know, observations telling us, and now also increasingly simulation, is that in the center, elliptical galaxy would form. And then throughout the cluster, you'll find a mix of ellipticals and spirals in those little peaks. That would be satellite galaxies, so it makes a cluster of galaxies, but could be a mix of different morphologies. So I lost track. When did I start? What time? How much time do I have left?
8 minutes.
8 minutes? Okay. Okay, so again, this is just to remind you that the reason those two objects without any dissipation look similar, because again, these Gaussian fields look similar. So statistics of perturbations on different scales that go into when peak collapses. So in other words, if we take this peak on a scale corresponding to the 10 to the 12 solar mass object, and we take this peak that corresponds to 10 to the 15 solar mass object, statistically here they're made to be very similar by using the same random seed. Different regions would have different small scale structure, but statistically they would be very similar, and the main difference between them would be just overall amplitude between them, the starting overall amplitude. Right, but that's why the final structure looks very similar, because they are statistically the structure within these peaks is quite similar. Right, again, the same point. Okay, so but there are deviations from some similarity, and also the main difference is reflected by the fact that the typical amplitude of perturbations on those different scales are different. So a scale here on clusters is on average the amplitude is smaller than on the galactic scale. So let's see what consequence it has for the mass assembly history of halo. So I showed you evolution of matter in the collapse of this halo. So how do we measure mass assembly history in simulations like this? We have to go back into the density field sampled by particles, or by particles in this case in the simulation. We have to identify peaks in density field. And we have to define mass somehow. And what's usually done is that once we find a local peak of density, that peak is surrounded by a sphere of a given radius. And this radius is defined to be the radius that encloses a given density contrast. So this is a different delta. So this is not a small delta, it's a capital delta, Greek. And that's because this delta is defined not as rho minus rho mean divided by rho mean, but simply as rho divided by rho mean. So it's a not over density, but density contrast. It's just ratio of densities. Source dimensional quantity, but defined somewhat different. And the typical value that's used for this is 200, so 200 relative to mean, with some variations. Motivation for this is pretty loosely based on predictions of so-called spherical collapse model that we'll talk about later. But and you'll find in this notebook, you can find specific derivation for why within this spherical collapse model you expect the density contrast of collapsed object in the largest extent to be of order 200. But this motivation is very loose, so mostly you can think about as semi-arbitrary definition. But nevertheless, this is a typical value that's used, and also because it's semi-arbitrary in the literature, you'll find a range of values that people choose to use, which is very confusing, sometimes mind-boggling, but It's just a fact of life that in the literature you'll find different definitions, but I'll use for what follows the definition that you see here. So it's density contrast of 200 relative to the mean density of the universe. So effectively, we grow a sphere around a given density peak, and we find a radius within which the density contrast delta is 200 times the mean. We declare this to be a boundary of the halo, and the mass enclosed by this radius is the mass associated with the peak. And schematically, it's shown here. Then, as we go to higher redshifts, of course, the mass assembled in this peak, as we already just discussed, is actually spread out through filaments, so other halos, and so on, so on, so on. But that mass is not counted. Rather, we choose the most massive progenitor of the peak. So we look at all the collapsed peaks that end up in this final sphere. We choose the most massive one at which reaches so-called main progenitor, and we measure the mass of that progenitor. And so the evolution along this main path is called the mass assembly history or mass accretion history. So everything else is co-evolving until it joins these most massive objects through accretion or merger. And we account for it at that time as additional mass that joins the object. But the mass it traces is tracing the mass of the main progenitor. It's like we would look at the main galaxies that turned into the Milky Way without counting its smallest neighbors until they actually accrete onto it. Any questions?
What is the accuracy in your simulations? I mean, what is the lowest scale?
In this case, these simulations have low scales of about kiloparsec, well, few kiloparsecs. So this particular simulation was resolving this object with a few million particles, and at the end, the resolution was about probably 1% of this radius that you see here, so 100 times smaller than this sphere. Okay, so here are the actual measurements from simulations like this, where you see the mass of the main progenitor measured at different times as simulation evolves for different objects. So these are different collapsed halos that collapse in different parts of the volume. And they are selected to be about 10 to the 12 solar masses at redshift 0. So the objects in different places that end up with a similar mass of 10 to 12 solar masses were selected, and they are shown here each by a line, just to see what range of evolutionary histories you have. There are two panels that show you exactly the same thing. So they are the same lines, but in this panel, the scale of time is logarithmic. It shows the early time evolution better. In this case, the scale in time is linear, which gives more justice to the actual running of time. The running of time is logarithmic, although with age, I start to question this. But if we assume that time is linear, this highlights the fact that majority of mass accretion, mass assembly happens during early times, whereas during the last few billion years, the mass changes much slower. And this is also the reason why people talk, when they discuss mass assembly histories, they talk about fast accretion regime here and slow accretion regime separated by formation epoch of the halo. And you can clearly see it here, that the time derivative here would be considerably larger than time derivative here. So there's very, very fast growth, several orders of magnitude within a couple of billion years, and then much slower, much milder growth, maybe tens of % over the last 10 billion years of evolution. You can see that majority of these objects behave quite similarly, right? They trace sort of a mean behavior that looks like this, with some scatter. That reflects the fact that these objects start under different conditions and have different realizations of a Gaussian field in their neighborhood that result in different collapse of peaks, different merging timing, different evolution. But just by design, by selection, they're all selected to be around 10 to 12 at the very last time. So this gives us an idea that the collapse of different peaks can be traced by a smooth function, which we'll try to understand why it's the way it is and why there are these two regimes. And at the same time, it tells us that there is some scatter. So when we look at objects of a given mass, there is some variation in the evolutionary histories that reflect the difference in initial conditions that translate into differences in evolution. So this is 10 to 12 objects, 10 to 12 solar masses, and this is the 10 to 14, right? So the same thing, but now selected to be 10 to 14 at redshift 0. Do you see differences? So again, here's 10 to the 12, 10 to the 14. Do you see any obvious differences? It's probably not that easy because I'm not showing you them side by side. I'm just cycling, but
the range is bigger.
The scatter is bigger.
the scatter is somewhat bigger, although here I'm just showing 20 objects, not to overwhelm your senses. And so there's some difference maybe just because there's a couple of objects like this. But there was one correct observation that the range is bigger. So if you look at this object, you can see it changing by more than 2 orders of magnitude in this time frame. And this time frame is actually, oh, sorry, yeah, this is not. This time frame is the same in the two plots. And so here you see that these curves break. This is actually a resolution, limited resolution effect, because it becomes hard to find halos below certain mass, below this mass. That reflects a limited mass resolution, the fact that particles have some mass and we cannot resolve halos below certain mass. Whereas in the cluster scale, we could trace the evolution to larger. But that could be just a resolution. But if you look at this linear scale, you can kind of see that in galaxy case, the increase here was much more like a wall, much more rapid compared to increase here, right? So in other words, this evolution is kind of more gradual at low reaches, so it's has somewhat different shape. But the difference is subtle, right? And so even the fact, and most of the difference is just due to the fact that the typical fluctuation amplitude on a cluster scale and galaxy scale is different as given by the sigma values. We're not taking a difference from the slope of the sigma as a function of scale, just a difference of values in sigma. That's the main difference here, and it's already quite subtle. It's easier to see if we actually construct a median for each of these curves. So in other words, I'm looking at the scatter, and I'm determining different times, I determine the median of these different lines, and then smoothing it a little bit so that just random noise gets removed, and this is the medians. And for different final masses. And here the final mass is taken away, so they're normalized to the final mass, so they all end up at 1. And you can see that the cluster scale objects that are shown by this light curve, 10 to 14, are systematically different from a small scale objects, 10 to 11. So the overall shape is very similar, but there are subtle differences between the curve. And the subtle difference is mainly reflecting the difference in the sigma value on those different scales. So the fact that sigma is different, which means that the typical cluster had a smaller initial amplitude, so it could not have assembled as much mass as the galaxy, simply because it had to have more time to grow from a smaller initial amplitude. And so it had to form later, had to assemble its mass later to make up for this fact. And that's why this curve is lower than this curve. We can also notice that, and that's something that's noticed here, so they're almost the same but with a small difference, but we can also notice that this curve that has the largest m in these rescaled units at a given time is also the shallowest, which means that its m dot is smaller. So we can reasonably guess that if we actually take a ratio of mass at a given time and m dot, the difference between curves would be smaller. And that's actually what happens. So this is what I call the accretion time scale. So this is mass of the object at a given time divided by accretion time. So this quantity has units of time because mass scales out, and the only thing that's left is time derivative, so inverse time. So divided by inverse time is time, so in giga-years. So this tells you the typical doubling time scale in giga-years for halos of different mass as a function of time. And it grows with time, which means that doubling time was very fast, a fraction of billion year early on, and then becomes of order the age of the universe close to redshift 0. But you can see that the difference between different masses almost disappeared. It became less than a factor of 2. It's still there, but became less than a factor of 2. In this case, I took out the main difference in the average amplitude of the initial amplitude, and I only left the difference that's due to the difference in the slope of the sigma, the slope of the power spectrum and the slope of the RMS fluctuations on two different scales. And you can see that the result, the differences become very, very subtle. So this difference in slope are subtle, but they're still there and are quite noticeable. So I'll end with this, and I'll show you that the last point that I'm going to make is that these are results of simulations, and this you saw an illustration of how we can go into simulation and can measure how halos assemble their mass as a function of time. We can make a simple analysis. By the way, all the data files and all the plotting routines that you saw in these slides, you'll find in the practical exercise in the notebook X01, where these medians are constructed, and the plots that you saw here you'll find in that notebook. And you'll also find comparison in the notebook with this approximation. It comes from Kravtsov and actually is based on a few papers by Deckel and Nystein, which approximate this complicated behavior by a simple fitting function, which looks like this, which is a power law function of mass with some growth factor, linear growth factors involved and time derivative of it. And this type of approximation is used very frequently in modeling of galaxies, so simple estimates. And it's an example where simulation results are translated into useful and simple phenomenological fitting formulae. Other examples of them from recent papers you can find here. Again, they approximate the m dot, so growth of mass in units of mass, but you can divide it by m and turn it into accretion time if you want. And you can find such approximation in the literature. This is a relatively recent result based on Eagle simulation. And in this case, you can see that they only parameterize as a function of mass linearly. So if I divide mass by accretion rate, the resulting equation has no mass dependence, which means that this approximation actually predicts that all of these lines should have coincided, right? There should be no difference. So right away, you can kind of tell that it's not quite right because the simulation tells you that there is a subtle difference, which you can also expect from the fact that the slope of sigma r is different. But you know, this approximation neglects this difference, which means that it's quite subtle. So this is an example of when complicated simulation results are turned into simplified but useful phenomenological fitting formulae. I'll ask you to play with this fitting formula in exercise number 1, and I'll stop here, and tomorrow we'll try to make sense of why the accretion histories look the way they are, and why these crocodiles that look like complicated, some arbitrary fitting functions, why they have the shape they have. Thank you, and let's ask some questions. Yeah.
What happens if we use the real radius instead of the radius relies on predefined density contrast?
Fixed density contrast. Okay, so the question is, let me repeat the question, and I'll try to see if I understand it correctly. So the question was, what happens if we use the virial over density as opposed to the fixed density contrast, which refers to this definition. No, I already think. No, let me find it because it will be clearer. No, maybe easier if I find it. So the question was, what if I change the mass definition of halos and recalculated the mass accretion history? Yeah. If I understand it correctly, right? So
especially if we use the virial radius.
So you mean that if, instead of using the fixed delta, if I use the delta that changes
based on the virial theorem.
Based on the virial theorem, yeah. So so like I say here, the motivation for using a number like 200 here loosely comes from the prediction of a spherical collapse model, that details of which you can find in this notebook, and also why there is a motivation for this number, which is so-called virial over density. And for omega, for universe, for cosmology with omega 1 and no lambda, this virial over density is predicted to be 178. It's actually 18 pi squared. It's like a fundamental constant, 18 pi squared, which is close to 178, but people usually just round it up to 200. So use 200. And in a universe without cosmological constant in which omega matter is 1, that number is the same at all reaches, right? So you can use a constant. So if you wish, this choice of using 200 and having it constant kind of neglects the fact that we are living in lambda CDM universe. So let's just use the contrast predicted for so-called Einstein de Sitter omega 1 universe and keep it constant. So the question is, what if we actually use correct prediction for cosmology that we are simulating here, in which case this number, first of all, would not be 200, and also would be redshift dependent. Redshift 0, that number would be of order 365 for this cosmology, or thereabouts, so not 200 but higher. And at higher redshift, however, it would actually converge to this number. So redshift about 3 and higher, because omega matter at those redshifts is close to 1. The number would go from 360 to about 200. But
what's the different question?
Different?
If you use virial theory, not approximation.
So that was the question. So instead of the virial over density, that's why I was trying to understand whether I actually got the question. So yeah, so then forget about what I said. Although what I said is relevant, because in the literature you'll find different mass definition with where delta has a little subscript called vir, delta vir, where people actually use virial density contrast that depends on time, a function of time, not constant as used here. In which case, for understanding what's going on there, they call it virial, but they motivate by exact prediction of spherical collapse model for non-omega 1 cosmology. If the question was, what if we use the virial theorem to define the mass? It really depends on how you would apply the virial theorem. If you actually tried to look at how virial theorem applies at different radii, would check. So for example, if I understand correctly, you're thinking about checking how well virial theorem applies at different radius, then finding the radius where it breaks, right? And then defining mass there. So it turns out that radius for many of these objects, in particular objects that are 10 to the 12 and smaller at redshift 0, is not easy to identify. So if you do a simulation, in other words, you look at mass in for equilibrium, and you find that mass is in equilibrium almost at all radii until it joins into expansion of the universe. Actually, Anatoly wrote a few papers on this. It's difficult. That's one of the reasons why people use simpler definitions like this. I can tell you more details and actually show you plots to support what I say, but in practice, this definition is not easy. There is a different definition related to so-called splashback radius. It's a radius corresponding to upper centers of the matter that had just one time to reach the upper center. That radius is more easily identifiable. And it's a more physical radius compared to this. And there is work has been done to see how masses defined in this way would be different. But virial theorem is difficult to apply in general.
You can do it, but the same.
You can do it, but not easy.
It has the same accuracy as those approximations. And the reason for that, like a virial theorem, you assume like stationary system. This is not exactly, and you need to correct for the boundary, the pressure on the boundary, because it's not isolated object. So at the end of the day, it gives you the same accuracy. Results are not different, and that's easy to apply. I will give a lecture on structured dark matter halos, and we'll see that.
Also, I can just add to answer your question. The results would not be qualitatively different. So you'll find some numerical differences. Maybe lines would be somewhat different shape, but it would be subtle difference. Qualitatively, you'll find the same result if you go to a different definition closer to what you're thinking about. People ready for coffee? Yeah.
How will the mass accretion history change if we consider warm dark matter?
Warm dark matter. It's a very good question. So what would happen, by a warm dark, so the question is how the mass accretion histories would change if we, instead of assuming cold dark matter, meaning that we completely neglect any velocities at any time for dark matter particles, which means that structure in pretty much all the scales that are relevant for galaxy formation is present in the perturbation. We change this assumption to so-called warm dark matter, where particles can have non-zero velocities during early stages, which could erase perturbations below a certain scale. So for those models, people have simulated these models, and for those models on a scale corresponding to the typical streaming scales of the particles, below which the perturbations have been erased, the formation of objects below that scale is almost suppressed.
There's some arguments about that some of them, some of the small scale objects below that scale could form by fragmentation, but majority of collapse is completely suppressed simply because you erase delta. You erase the initial overdensity. On larger scales, when you're close to that scale, the formation of a halo would be delayed, so it would collapse later. So the mass accretion histories for galactic objects would look more like clusters. But the larger, the more you go away from that scale, the less difference you'll see. So if warm dark matter has masses below the currently constrained limits, for the majority of galaxies you would find almost extremely small difference. And only for the smallest dwarf galaxy it could be relevant. So for the purposes of gross overview and understanding how galaxies form, from what we currently know from the observational constraints, you can forget about warm dark matter, mostly.